All right, so let's try to use that technique of building up a solid from a series of disks and show that the volume of a sphere is 4/3 pi r cubed. Okay, so that's probably a formula that you learned at some point in your education, but we're going to show how to get that formula using this technique. All right, so what I'm going to do here, now essentially a sphere, let me just draw, first I'll draw a circle. These problems start getting very tricky because you have to draw in 3 dimensions. So if I draw a circle, okay, you know, that's kind of the cross-section of a sphere or the shadow of a sphere. But this circle really has 3 dimensions. I'm going to first of all just draw this in a plane. Okay, so I'm going to superimpose an XY plane here. Let me see if I can divide this fairly closely. So here's Y and here's X. And the equation for this circle, you know, is just x squared plus y squared equals r squared. Okay, so we're using just some generic r value. This r could be, you know, we could have a radius of 1 or 2 or 3 or 5 or whatever we want, but we're just going to try to derive this general equation with x equals r, or sorry, r, just using r. Okay, so we have x squared plus y squared equals r. Okay, so this circle then goes from r to minus r in the x direction, and also from r to minus r in the y direction. All right, and what we're going to try to do is think of this as, you know, being, actually we only have to rotate half the circle around to get the sphere, and then we'll get a series of disks. So if I take one particular disk, I'm just going to use this as the radius of one particular disk, then it looks sort of like, let's see if I can draw this fairly decently. Okay, hopefully you get the idea. It's hard to draw these things. All right, and then I'm going to give it some thickness. All right. All right, so it looks like a coin. It kind of looks like a, it looks sort of like that. Okay, so there's one disk. And the radius essentially is the y value in, you know, at this particular point. And for this particular actually x value. And then the thickness is delta x, right? So we have these disks, right? All right, so now we want the y value because that's going to be our radius. So let's rearrange this equation. X squared plus y squared equals r squared, right? That's the equation for a circle. So if we solve for y, we get y squared is equal to r squared minus x squared. Now I know that I don't actually need y, I need actually y squared, because the cross-sectional area of this disk is going to be pi r squared, where r is y, and so what I really need is y squared. So I'm just going to leave it that way. And so then what we can do is just add up all of these little disks. So we're going to integrate from minus r to r, and we're going to have pi r squared. So this is a different r. The r of the disk is y, right? So we're going to have r squared minus x squared is the radius of any given disk, right? And then we take it times dx, which is the thickness of the disk. Okay? And so if we integrate that, we'll get the volume of the sphere. So, well, this seems to be easy enough to integrate. So actually I don't need that anymore, do I? I can just evaluate this integral. Now r, for any given sphere, is just going to be a constant. So we're really integrating it with respect to x. So with respect to x, r is just a constant. So I'm going to pull the pi out front, and then if r is a constant, then when we integrate r squared, we just get r squared x. Okay, just remember r is constant, and we're integrating with respect to x. All right, so and then when we integrate x squared, we're going to get 1/3. So minus 1/3 x cubed. And we're going to evaluate that from minus r to r. All right. Now I should mention too, we could just integrate from 0 to r and double it. Actually, it's a little bit easier that way. But we'll just go ahead, since I set it up this way, it will integrate from minus r to r. All right, so let's plug in those r values and see what happens. All right, so we have pi, and then times r squared times r minus 1/3 r cubed. So I'm just plugging in r in place of x. All right, so that's the evaluating this at the upper limit of integration, and then we're going to subtract this thing evaluated at minus r. So we're going to get r squared times minus r, okay, minus 1/3, and then we're going to take minus r and cube it. All right, so what have we got here? We have pi. Let's see if we can combine some of these things. Because r squared times r is r cubed. R squared times minus r is minus r cubed, but then we're subtracting it, so it really becomes plus r cubed. So we have plus r cubed plus r cubed. So we have 2r cubed, right? And then we have minus 1/3 r cubed, and then minus a minus minus r cubed. So we got 3 minuses in here, because when we cube negative r cubed, we're going to get negative of r cubed, and then minus that becomes positive, but then we're subtracting again. So this becomes minus, and we have 2 of them, right? We have this minus 1/3 r cubed, and we have this minus 1/3 r cubed. So we have minus 2/3 r cubed. All right, well, that's easy enough. So 2 minus 2/3, so that's 6/3 minus 2/3 is 4/3. So we end up with 4/3 pi, and then we have r cubed, which is what we wanted, right? That is the volume of a sphere. I should also mention too that we could have integrated this another way. We could have taken horizontal slices. And that's actually what we're going to do in the next problem. We're going to look at an example using horizontal slices instead of vertical slices.